We will now progress from our study of differentiation of natural logarithms and integrals involving natural logarithms to differentiation and integration of the natural exponential function. But before we jump into the calculus, we're going to examine an important application involving the logistic growth model. Definition: many populations grow according to the logistic model P of t equals a over 1 plus be to the negative kt, where a, b, and k are real number parameters. So the pattern of this function is often used to model growing populations. These populations may be the populations of deer on an island or the populations of tumors in a growing cancer cell. For example, if we backtrack just a minute to the previous section, we solved a differential equation at the end of section 7.2b. And the result that we came up with, believe it or not, was a logistic growth model. Our result did not necessarily fit the exact mold of the logistic growth model, but we could rewrite it in the pattern of the logistic growth model presentation there. So I'm going to go back to our solution y of t, and I'm going to divide everything in this function by c e to the t. So every single term gets divided by c e to the t. And when we simplify, we end up with 1 over. Now, right here, as we saw with manipulating the constant, the changing constant here, we said e to the c equals c. We had 2 times c equals c. We can also see that this coefficient 1 over c, that's just going to make a new constant. 1 divided by a constant is a constant. And then we can rewrite that e to the t in the denominator as e to the negative t. Then you can see we have a 1 in the numerator, which matches a constant in the numerator. We have a constant times an exponential with a negative exponent. That matches this term here. And finally, we have plus 1, which matches the plus 1 here. So this is a form of the logistic model that we are studying. Let's look at another example to examine the behavior of this logistic growth model. Example 1. Consider P of t equals 500 over 1 plus 83.33 e to the negative 0.162 t, where P is the number of bald eagles after t years. So we're looking at a population of bald eagles, and t is going to be our independent variable measuring time in years. Let's see if we can answer the questions about this logistic growth model. What is the initial population of eagles? Well, when we start this model, we're looking at 0 years. So we need to calculate P of 0. That is, we're going to plug 0 in for t. Now, we know that e to the 0th power here is equal to 1. So we can simplify this to 500 over 1 plus 83.33. Or how about 500 over 84.33? Now, when we type that into our calculator, we're going to end up with 5.9, but we know we can't have 0.9 eagles, and we don't want to round up, so we're going to go ahead and round down. Again, the calculator produces 5.9, but since we're dealing with whole eagles here, we're going to give a conservative result, which is 5 eagles. So at the beginning of this population model, we are starting with a population of 5 eagles at time 0. The next question says, what is the carrying capacity of the population? So generally with logistic models, the population begins growing slowly, it explodes over time, and then it hits a steady state solution. So if you type this function into your calculator, you'll be able to see the general behavior of this curve. So on the horizontal axis, we have time in years, and on the vertical axis, we have the population of eagles. On your calculator, you'll see that the curve begins to grow slowly, and then it explodes, hits a bit of an inflection point, and then it levels out over time. So the carrying capacity of the environment basically it's looking for what is this horizontal asymptote under which the curve begins to level out. The carrying capacity is generally dependent on environmental conditions, the availability of food, the potential to build shelter, the presence of predators in the area. So what does this mean mathematically? We want to know what's the population over time. Well, if we want to know the long-term population, we can calculate the limit as t approaches infinity of our population function. That is, the limit as t approaches infinity. So as time increases without bounds, what's the limit of our logistic function? Write that clearly. So if we apply the limit to our exponential function, e raised to a negative exponent as t approaches infinity eventually goes to 0. So we have the limit as t approaches infinity of 500 over 1 plus 0, which very easily is 500. So the carrying capacity of this particular population is 500 eagles. So on our graph, that means that this horizontal asymptote occurs at p equals 500. So the population grows slowly at first, explodes into what resembles exponential growth, but then it levels out under that steady state carrying capacity. Now, the carrying capacity, of course, is dependent on the model, and that's what these parameters are dependent upon. The way that one designs this model, again, is reflective of the environment or the habitat of those eagles. Next question, when will the population be 100 eagles? So the question of when here basically means I'm looking for t. When will the population be 100 eagles? That's giving me the p-value. So we can say if our population is equal to 100, we need to solve this equation for t. So the first thing I'm going to do is multiply both sides by that denominator. Then we can divide both sides by 100. Whoops, I have a parenthesis in the wrong place here. So 500 divided by 100 is 5. We could then subtract 1 from both sides. Then we would divide both sides by 83.33. Now I'm not going to carry that out on my calculator yet. I don't want to round here and then again in a minute I'm going to build up too much rounding error. So I'm going to postpone the rounding to the very last step. Now this is an exponential equation. You can solve this by converting it into log form. Notice the base here is e, so we're going to need a natural logarithm. We're going to take log of 4 over 83.33, and that's equal to our exponent. Just the exponent there, not the base e. So again, what am I doing here? I'm just going from exponential form. So you have e to the x equals y, just to establish the pattern here. And we're rewriting this in the form of a natural logarithm. So that's natural log of y equals x. So converting between forms. Now to finish solving for t, we need to divide both sides by negative 0.162. I'm going to flip my t over here to the left side. So our exact answer here is natural log of 4 divided by 83.33 over negative 0.162. Now if we enter that into our calculator, we're going to be able to approximate, and let's just go to the nearest year. This would be approximately 19 years. Now the problem didn't tell me where to round. I'm not using the principle of significant digits. I'm just arbitrarily rounding here. So after about 19 years, the population will be 100 eagles. And remember, the carrying capacity of the entire population is 500 eagles. So back on the graph, you'll see that that's really close to the inflection point. About 19 years, we have 100 eagles, and the graph that I have here approximately goes out 100 years. So of course not drawn to scale. You can examine that with your calculator. But this is an example of a logistic growth model, and as you'll see from differential equations, this particular model pops up quite often in terms of exponential growth, specifically measuring population growth. All right, in the next video, we'll get started on derivatives and integrals of the exponential function.